Welcome to EFIWE Excellence Without Stress.
Hi, dearest EFIWEs. Our excellence journey continues today, and our topic today is dispersion of light. Dispersion, just as the name implies, it's just as if you are breaking down or you are distributing light into different segments. So, what is dispersion? Dispersion of light is what we call the phenomenon that arises as a result of the dependence of the refractive index on the wavelength, that is, phenomena in which white light is split into individual colors during the passage of light through a substance. So just imagine, let's look at this picture. It's so simple. You know, we talked about refraction. I told you that refraction occurs between two mediums. It occurs between two mediums, not just one. When light is going from one medium to another, then refraction occurs. It's called the bending of light rays when light is moving from one medium to another. So this is the white light coming from somewhere. We don't know where it's coming from, but when it came across this triangular prism, there was a splitting. Yes, so this is just telling us that inside white light we have all the colors, the Roy-Beef, red, orange, yellow, green, blue, indigo, and violet. So white light entering this medium, which is this triangular prism of light, when it entered, there was a splitting occurred, and that splitting is what is called the dispersion of white light. That is, white light consists of all of this. So when we had all of this together, we have the white light. So when we are saying dark, it means it's the absence of what? Of white light. It means we can't see any of this color. So as we're saying, the cause of dispersion is the dependence of the phase velocity of the light wave propagation on its wavelength when passing through a material environment. So this is the simplest definition. Dispersion of light is just the breakdown of electromagnetic radiation into components at different wavelengths. You're going to understand that as we go. So again, dispersion of light is the breakdown of electromagnetic radiation into components at different wavelengths. So formation of rainbow. So how is rainbow formed? What causes the formation of rainbow? What causes rainbow? So rainbows are formed by the dispersion of light and reflection, not total internal reflection. Don't worry, you understand what total internal reflection means later on. From drops of water. Let's look at this, please. Always look at the direction. So this is a drop of water, right? And this is light. So the light from the sun came and touched what? This drop of water, and what happened? It broke down into what we call the rainbow, and that's what we see. So look at it now. This light was coming from here, this place. Now the light was in the air, but when it entered another medium, this medium is water. So this is less dense, this is denser than this. So refractive index occurs when light moves from either a denser to a less dense, or a less dense to a denser. So this is refraction, bending. So this one was coming from a less dense to a denser, which is the water. Then refraction what occurs. After refraction has occurred, what happened? The reflection, and that is what we see as the observer. Is that clear? So rainbows are formed by the dispersion of light and reflection. Yes, look at it. Dispersion. Refraction occurred, which led to the dispersion, just like we saw in that triangular prism. Then this is which reflected back, and that is what we are seeing. When sunlight enters a raindrop, look at the way you are seeing. This is the direction. When sunlight enters a raindrop, it is refracted. Yes, refraction, refracted. Why? Because of the fact that this light ray has moved from one medium to another. It moved from a less dense medium to a denser medium, and that is it. So when sunlight enters a raindrop, it is refracted and dispersed into its component colors due to the different wavelengths of each color. Every color has its individual wavelength. The light is then reflected off the back of the raindrop and refracted again as it exits the raindrop, creating a circular arc of colors in the sky. This is what we see. The color of the rainbow are always in the same order: red, orange, yellow, green, blue, indigo, and violet. The acronym Roy-Beef can be used to remember the order of the colors. Don't forget Roy-Beef. The splitting of white light, it splits into what? Roy-Beef. So the visible light spectrum, this is it. The visible light spectrum is a segment of the electromagnetic spectrum. So this is the electromagnetic spectrum. We cannot view. You cannot view the radio waves. You cannot see the microwaves, the infrared, no. Ultraviolet rays, no. X-rays, gamma rays, no. But there's just one part, which is called the visible light. This is the part. So this is the electromagnetic spectrum. But there's only one part that we can view, and that's this thing. So let's continue. Say visible light spectrum is a segment of the electromagnetic spectrum that the human eye can view. More simply, this range of wavelength is called the visible light. Typically, the human eye can detect wavelengths from 380. Have you seen that? That's the one for violet. Violet started from 380 to 450, from to 700 nanometers. Yes, nanometers. You know the wavelength is actually in meters, but this one is in nanometers. Nanometers, yes. That's times 10 to the power 9 or minus 9. Okay, nanometers. From 380 to 700 nanometers. So this for the violet is 380 to 450. For the blue, 450 to 485 nanometers. Those are their wavelengths. So these are the only part of the electromagnetic spectrum that we can see, and it is called the visible light, just as it is. So the visible light spectrum is a segment of the electromagnetic spectrum that the human eye can view. More simply, this range of wavelength is called the visible light. Don't forget what we talked about. The visible, that's also the Roig beam, the splitting of white light. The addition of red, orange, yellow, green, cyan, blue, and violet is going to give you what? White. So let's proceed. So, and this is the same thing we're still talking about. So visible light spectrum, when all the wavelengths of the visible light spectrum strike your eyes at the same time, white is perceived. So just understand that anytime you are seeing white, what has happened is all the visible lights, the Roig beam, are eating your eyes at the same time. All of them are eating your eyes, and that is why you are seeing white color. So when all the wavelengths of the visible light spectrum strike your eye at the same time, white is perceived. The sensation of white is not the result of the single color of light. No, it's not possible. White is not just a color. Rather, the sensation of white is the result of the mixture of two or more colors of light. Thus, visible light, the mix of Roig beam, is sometimes referred to as white light. So Roig beam can also be called white light, because when you mix all of this together, you are going to get what? White light. White is a combination of all colors of the visible light spectrum. You know, we talked about the visible light spectrum, which is the Roig beam. If all the wavelengths of the visible light spectrum give the appearance of white, then none of the wavelengths will lead to the appearance of black. So once more, black is not actually a color. Please know that black is not a color. Technically speaking, black is merely the absence of the wavelength of the visible light spectrum, just the absence. It's not as if it's actually a color. But when we can't get any wavelength of the visible light, then we have black. So when you are in a room with no light and everything around you appears black, it means that there is no wavelength, don't forget that, of visible light striking your eyes as you sight at the surrounding. So you remember your primary colors from your secondary, your primary school and all. So you have the red, the green, and the blue. Addition of these three too will still give you what? White. Yes, they say there are a variety set of primary colors. The most common set of primary color is red, green, and blue. When red, green, and blue lights are mixed or added together with the proper intensity, white light is what? Obtained. This is often represented by the equation as R plus G plus B is equals to what? White. In fact, the mixing together of two or three of these primary colors of light with varying degrees of intensity can produce a wide range of other colors. So additive colors. So look at it now. We have the primary colors, which is what? Yellow, blue, and what? No, sorry, red, blue, and green. Those are the primary colors. Red and green will give you yellow, right? Red and blue will give you magenta. Then what? Green and blue will give you cyan. There's something else you need to know. This magenta and green, all these opposite colors too, will still give us white. Yellow and blue will give you white. Red and cyan will also what? Will give you white. So that's just what the additive color is all about. So complementary colors of light. Any two colors of light that when mixed in equal intensity produce white are said to be complementary colors to each other. So simple. So anytime you hear complementary colors of light, any two colors that when you mix them together, they give you white. They are called complementary. So R plus C, R plus B plus G all gives us white are called what? Complementary colors of light. Electromagnetic waves and their spectra. So these are electromagnetic waves, different electromagnetic waves. So electromagnetic waves are waves that are capable of traveling through a vacuum. Don't forget that when we talked about electromagnetic waves, they are waves that do not require material medium for their propagation. Remember that the opposite of electromagnetic wave is the mechanical waves that requires what? Material medium for its own propagation. So electromagnetic waves are capable of transporting energy through vacuum of outer space. Remember when we were talking about sound and we did the experiment on sound where we're using the what? The electric bell jar where we took air out of it, and we noticed that although the hammer was still hitting the gong, we're not hearing any sound, because sound is a mechanical wave. But electromagnetic waves are what? They do not need material medium for their own propagation. So electromagnetic waves are produced by vibrating electric charge, and as such they consist of both an electric and a magnetic component. Electromagnetic wave exists with an enormous range of frequencies. Yes, different frequencies. The entire range of the spectrum is often broken into specific region. So let's just go. We'll see the electromagnetic. So this is the electromagnetic spectrum. Don't forget that your C, which is the word speed of light, is 3 times 10 raised to power 8 meter per second, and this is the electromagnetic wave spectrum. You know, we remember we have the visible light. That's the only part that we can see. All these other parts we cannot see. So don't forget your C is equals to lambda f. So each of these ones too, their speed can be gotten by what? Lambda f. So the higher the wavelength, the lesser the frequency, and that's the lesser their energy. Don't forget that. So gamma ray has very little wavelength, but the frequency is so high. And look at what this thing here. Frequency is proportional to energy. The more the frequency, the more the energy. But look at X-ray also has more what? Frequency than the what? The radio wave. Are we getting that now? So radio wave has the highest wavelength but the smallest frequency, and with that it also has the smallest what? Energy. So looking at this now, if we're talking about the frequency moves from radio to micro to infrared to visible light to ultraviolet to X-ray and to gamma ray. So that's the direction of the frequency, while the direction of the wavelength is from gamma ray. That is, gamma ray has the lowest wavelength. X-ray, ultraviolet, visible, infrared, microwave, and the what? And the radio. You see that the only thing we can see here is the visible light. The other thing, there is nothing to show, because we cannot see it with our what? With our naked eyes. We cannot see them with our naked eye. So just as this thing has written, the higher energy is with gamma ray. So gamma ray can penetrate lead. Is a very, very strong type of ray, because it has the highest frequency and the highest energy. So that's about the electromagnetic spectrum. So electromagnetic waves, we have the radio waves. So these are their what? Their wavelength. Don't forget, I told you that the gamma ray has the lowest what? Wavelength, but the highest frequency. And you know, and the highest energy. Frequency is proportional to the energy. The higher the frequency, the higher the energy. So look at now the radio wave. Yes, big what's it called? Wavelength greater than 1 what? mm. So what do we use radio waves for? Broadcasting, communication, and navigation. Microwaves used for cooking, communication, and so on and so forth. Why the gamma ray is used for nuclear medicine, cancer treatment. It penetrates a lot. So that's about the electromagnetic rays. So, and this is the continuation. Electromagnetic radiation can be detected using various instruments such as the photographic film, Geiger counters, and spectrometers. This instrument works by detecting the energy of the electromagnetic radiation and converting it into a measurable signal. So spectrometers are used to measure the intensity of the radiation at different wavelengths. So that's that. Don't forget that. Allowing scientists to identify the composition of the source of the radiation. So thank you, and see you in the next class.